All right, welcome back, dedicated 131 students. You guys rock. All right, we're going to talk about VSEPR. It sounds like a whole mouthful, and it actually is. So valence shell electron pair repulsion. So it sounds impressive. All it's really saying is that electrons like to repel one another, right? Because they're negatively charged, and so electrons that are in the bonds, okay, they will repel lone pairs. And so, for instance, if we look at water's structure, Lewis structure, okay, what we're going to say in this section is instead of, a Lewis structure is kind of cool like that, okay, where, we have a kind of a linear looking molecule. What happens is these lone pairs, electrons in this lone pair will repel electrons that are in this bond. Okay, and what that does is it forces it, okay, so you get these repulsions here, and so it forces it into a bent structure. Okay, and so just because of these mutual electron-electron repulsion effects between bonding electrons and lone pair electrons, you'll get specific shapes. Okay, and so these also have a variety of steps, and so we're going to go through these steps, and then we'll go through a lot of examples for these. And so step one is to write a Lewis structure. Okay, I like that better. So just draw the Lewis structure as you saw in the previous video, okay, for the molecule. And then you're going to rely on really a table that we're going to talk about here to just predict the geometric arrangement, okay, assuming that the charged clouds are as far away from one another as possible. So what that means is that the geometry or the shape of the molecule is going to adopt a certain geometry or a shape based on the lowest amount of electron-electron repulsions. Okay, and so for instance, let's look at two charge clouds. Some books will call this electron pair domains. Okay, and what that really means is, to make it really, really easy for you, okay, are two things surrounding the central atom. Okay, so electron pair domains is kind of a fancy way of saying that there's two things around it. Okay, and so for CO2, its Lewis structure, if you were to figure it out, where you've got let's see, 16 total electrons, okay, and you're placing electrons around it, you would get a structure like this. So that would be your Lewis structure. And so what you're going to look at is you don't have any lone pairs on the central atom, and so you're not getting any repulsion between those electrons and the ones in the bond, and so as a result, this will just be a linear molecule. Okay, so for the case where you just have two things around the center, no lone pairs, okay, I will call this an AX2 type of molecule, okay, where the X are the just number of atoms surrounding the center, okay, and then L from all these different structures will be the number of lone pairs. Not individual atoms, but lone pairs, like two, okay, and these refer to just around the central atom. Okay, so we could care less. Notice for these molecules, you have a lone pair here on a peripheral atom, but that doesn't govern the shape. The shape is all about how many things you have around the center and if you have any lone pairs around the center. Okay, so both of these molecules, you have just one, two things around the center, no lone pairs, so they're both linear. Okay. Now, if you have three things, okay, let's look at the different shapes. Okay, so the possibility is where you've got three atoms and no lone pairs. And so I would describe this as AX3. Okay, so you just have, in this case, you've got an oxygen and two hydrogens around the center and no lone pairs. Okay. All right, so the geometry or the shape for this molecule, if it's in this type of system, would be trigonal planar. Okay, and a way to describe that is pretty well like a triangle, okay, where all of these angles are around 120 degrees. Okay, so they'll vary a little bit, so 122, 117, okay, but they're pretty well just like a triangle. And it's all on the plane of this paper too, so that's why it's trigonal planar. Okay, so now if you take, you still have three things around a center, but one of those things is a lone pair. You could call it AX2L. Okay, where now, for instance, you've got this one where you've got two atoms around a center and a lone pair. Okay, and so in this case, instead of it being trigonal planar, it's now, whoops, what did I do? Now it is just called bent. Okay, so AX2L is a bent geometry. Okay, so something like this. So two atoms and a lone pair around the central atom. Okay. All right, so let's look at four things around the center. All right, and the first thing is, or the first situation is where you have four atoms. So I would call this AX4. Okay. And this is tetrahedral. Okay, so AX4 is a tetrahedral shape. Okay, and one way that you can illustrate that, I don't know if these help at all. That's one way to illustrate a tetrahedron. Another way that some books will describe it, my limited artistic ability here, is if you have, let's say, carbon in the middle of a cube, and then the hydrogens are on alternate corners. Okay, so I don't know if if that is any clearer to you or anything, but kind of like alternate corners of a cube, that's also a tetrahedron. Okay, and so the angles around 109.5 degrees, okay, for a pure tetrahedron, okay. Now, what happens if you replace some of those with a lone pair? Okay, so this is the case where you have AX4, no lone pairs. This is the case where you've got three atoms and a lone pair. So I would call this AX3L. And the geometry here is trigonal, because you still have three atoms bonded to it, but instead of it being trigonal planar, it's now like a tripod shape. And so we would call this trigonal pyramidal. Okay? And in this case, now you've got two things bonded to it and two lone pairs. Okay? And this, the stereotypical case here is water, is this example. Okay? And this is just called bent. Okay? All right, so notice what happens when you have a lone pair. Okay, so these angles normally in a tetrahedron were about 109.5. As soon as you take one of these off and replace it with a lone pair, the angle now becomes 107 degrees, or it's smaller. And now if you have two lone pairs, you're really getting repulsion with these bonding electrons, so now the angle is even smaller. And so what happens is, if you have lone pairs, they take up a lot of space, and you tend to get quite a bit of repulsion with the bonding electrons, and so what that does is it closes in the angle in the structure. Okay. All right, so 5 things around a center. We would call this a trigonal bipyramidal structure. Okay, and this would be, I would call this AX5. Okay, and so since now you have 5 atoms bonded to a central atom, this has to be the A here, the central atom, has to be something in the 3rd row and beyond, because it has to have something that can exceed its octet. Okay, so things like phosphorus, so PX, so PCl5 is fine, but you'll never see carbon. Okay, so you won't have a carbon H5. Okay, that won't exist, or an NCl5 or something, that won't exist. Okay, but this can. Okay, PCl5, PF5, so all those are fine. Okay, and one way to describe this structure is it has, remember the trigonal planar was about 120 degrees, so think of this on the plane of this paper. You've got that trigonal pyramidal unit, or trigonal planar unit. Okay, so this triangle is on the plane of this paper, and now you've got one atom that's coming out at you, and then there's one that you can't see that's gone behind this paper. Okay, so that's these guys. One's coming out, one's going back. Okay, so that's one way to think about it, where this angle is 90 degrees and these angles are 120. Okay, so that's your trigonal bipyramidal structure. Okay, so again, this angle is 90 degrees. These angles are 120 degrees. Okay, so this is your AX5. Okay, if you replace one of these, let's say this one, with a lone pair, you get this one. Okay, and if you're to look at this shape, let me flip this 90 degrees here. I'll rotate it 90 degrees, okay, where you've got, a central atom, and now you've got the X's here. Okay, does that look like anything that you are familiar with? Oh, what a beautiful drawing here. This looks like a seesaw. Okay, so believe it or not, that is the scientific term for this geometry. Okay, if you have an AX4L, okay, where you have still 5 things around the center, but one of them is a lone pair, it's called a seesaw shape. Okay. Now, if you replace another one with a lone pair, so now you've got an AX3L2. Okay, so 2 lone pairs and 1, 2, 3 atoms bonded to a central atom. This is just called T-shaped. Okay, because it forms a T. Okay, this angle is 90 degrees, right? And then the easy one is if you have AX2L3. So now you will have 3 lone pairs and 2 things bonded to it. That's just called linear. Okay, so this angle will be 180 degrees. Okay, so for example, I3 minus is a linear molecule. Okay, and ClF3 is T-shaped. Okay, so that's where you have 5 things around a center. And the last one, so this is as far as we're going to go in 131, is with 6 things around it. You can go, so if you go on to take chemistry 331 or inorganic chemistry, we'll go all the way up to 9 and 10 things around it and different geometries there. So it can get more complicated. So let's just look at 6 things around it. Okay, and that is, I would call it AX6. Okay, and this is just called octahedral. Okay, and the reason why it's octahedral is because you can describe the shape really as you can have faces of an octahedron. Okay, so it's hard for me to show here, but if you were to kind of join, these and shade in, you will have this kind of a structure. And so this is called an octahedral structure, where all the bond angles, regardless of what they are, where they are, they're all 90 degrees. Okay. And so this is one example. And one way to think about it is you've got these four on the plane of the paper, and then maybe this one's coming out at you, that one's going behind. Okay. And so this is your AX6, where it's just an octahedral molecule. If you replace one of these, let's say that one with a lone pair, okay, now you've got, this is a square, right? So it's square, but you still have one sticking out, right? So this is forming a pyramid, so it's square pyramidal. Okay, and that would be your AX5L, okay, where you have 5 atoms bonded to a center and one lone pair. Okay. And then the last one, hooray, right, is you take away 2 of the atoms bonded, and now you've got 4 atoms bonded to a center, 2 lone pairs, and so this would be your AX4L2, and that's just square planar. Okay, so all these angles, 90 degrees, okay, and it's on the plane of this paper. Okay, so square planar. All right, so here is a really good summary sheet. Okay, so the number of charge clouds, electron pair domains, things, okay, if that makes more sense to you. Okay, so the number of, let's just do that. So number of things around the center, okay, around the central atom. Okay, so if you have 2 electron pair domains or 2 things, no lone pairs around the center, all you can have is linear. Okay, if you have 3 things around it, you have 2 possibilities. You have one where there's no lone pairs, and that's just your trigonal planar. So one example of that is BCl3, which the lone pair of BCl3 is this. Okay, and that's what I was talking about, that this is an exception. It's a group 13, so it's totally happy having less than 8 electrons. It only has 6 valence electrons around it, and it's fine. Okay, so this would have 3 things bonded to it, no lone pairs, so it's trigonal planar. Okay, if you have 2 atoms bonded to a center plus a lone pair, now it's bent. Okay, and then for the 4 series, you can either have no lone pairs, 1 lone pair, or 2 lone pairs on the center, and those shapes are tetrahedral, trigonal pyramidal for 1 lone pair, and bent if you have 2 lone pairs. So water is a bent structure. Okay. All right, moving on to the 5 series. Okay, so you can have shapes or molecules where you have 0, 1, 2, or 3 lone pairs. Okay, for the 0 lone pair, you have that trigonal bipyramidal, then it goes to seesaw with 1 lone pair. 2 lone pairs, it's now T-shaped, and 3, it now goes to linear. Okay, and then octahedral is if you have 6 things around a center, no lone pair. And then it goes with 1 lone pair, you have the square pyramid, and then it goes to square planar if you have 2 lone pairs. Okay? So that's really VSEPR. Okay, so looking at the kinds of questions to expect, I would just say, what about, let's say, this one? So what is the shape of this molecule? Or in this case, it's an ion. So this would be the sulfate anion. It's a negatively charged ion. Okay? So what is its shape? Okay, so the first thing you want to do with this to find out shape, I'm not going to explicitly say it in the question, but as soon as you hear or see the term, okay, what's its shape, know that the first step you have to do is its Lewis structure first. Okay, so never ever make an assumption saying that, oh, there's 4 things around it, so that has to be tetrahedral or something like that. Always, always draw its Lewis structures. Okay, so for this one, sulfate, we've got, let's see, so 24 valence electrons from the oxygen, another 6 from the sulfur, and then 2 more for the negative charge. So that's 32 valence electrons. Okay, so draw it out here. So we've got 8, 20, 26, 132. Okay. So now the question is this the right Lewis structure? So the beauty of VSEPR is that you really don't have to have the exact correct Lewis structure to figure out its shape. Okay, and so what I mean by that is, for shape purposes, it really doesn't matter if you have single bonds or double bonds. Okay, so if you're looking at this and saying, okay, is this a good Lewis structure? It's not the proper structure, because let's look at formal charges. Okay, if you figure out formal charges, all the oxygens are symmetrical. So you've got 6 for its valence minus 1 bond emanating from it, and then you've got another 6 dots around it. So each of these oxygens will be a -1 as far as formal charge. So what does that make the sulfur? It's 6 minus 4 bonds, and then you don't have any lone pairs, so that gives it as a 2, right? So again, it has to be plus or minus 1, no more. And so really the best Lewis structure for this is actually this. Okay, where I'm putting in 2 double bonds, okay? And so now if you look at sulfur is such where it can have more than 8, okay? So it can have more than 8. It's in the 3rd row and beyond, so that's cool. And so if you're looking at formal charges now, you've got sulfur with 6 minus 1, 2, 3, 4, 5, 6. So that's a 0, okay? These oxygens are a 0 formal charge. And so you just have minuses over there, okay, so for 2 oxygens. And then, you can do another resonance form, let's say, where the sulfur, the double bonds are here, let's say. Okay, and I'm not going to show all the other dots. Okay, or you could do it like here. Okay, so you have a wide variety of possible resonance forms here. Okay, so you can work out, how many total resonance forms there are for sulfate, but it really doesn't matter, right? Because even this one, if you're looking at VSEPR, hopefully you can see that, why did you rotate? Okay, so you can see in this form, I still have a central atom that's surrounded by 1, 2, 3, 4 things, right? No lone pairs around the center. And so this I would call an AX4, okay, because it doesn't have any lone pairs, and so that's tetrahedral. Okay, but if you forgot about, that it had other resonance forms, and you just went with this one, it's not the right Lewis structure. So if I'm asking, a question, what is the Lewis structure, then you should get into all these, talk about all the different resonance forms, etc. But if I'm asking for shape, it really doesn't matter. If you have this one versus the double bonded ones, this is still AX4, right? Because you don't have any lone pairs around the center. And so for shape purposes, you don't have to really fret over, okay, is there a double bond between the atoms? Is it singles? Is it doubles? Is it triples? It really doesn't matter. All that matters is how many things surround the center, how many things are bonded to the center, and if there are any lone pairs around the center. Okay? So hopefully that makes sense. Just like, the carbonate that we did before, I think in the previous video, I showed carbonate. And so that was one of these resonance forms as well. So, something like this. Okay. So to get it right, the proper Lewis structure is this plus others, we'll say. Okay. But if you just draw it like this, okay, do you still see this? I would call AX3 because there's no lone pairs around the carbon. This I would call as AX3 because there's no lone pairs around the carbon. Okay, so for shape purposes, this counts exactly the same as a single bond. Okay, it's just how many things or other atoms are bonded and then whether there are lone pairs. Okay. All right, so hopefully that brings some clarity to VSEPR. All right, so the last topic of this chapter is really dealing with valence bond theory. And this is, we're not going to get into really detailed calculations, so this gets really, really complicated mathematically. We're just going to do it really superficially and just kind of show you how to think about the electrons overlapping. Okay, and so this is just really trying to describe how electron pairs are shared in a covalent bond. Okay, and so the easiest example is the hydrogen molecule. Okay, and shown here, all hydrogen has, each individual hydrogen atom, you just have one electron in a 1s orbital. Okay, and so an easy way to think of it as is each of the hydrogens, you have one electron that can overlap. Okay, and they're shown as a spin up and a spin down, okay, so that they become paired. Okay, and so you remember when we were doing electronic configurations, if you had one electron in an orbital, the next one would come and it would be spin down, okay? The same when they're combining in this, we call it a molecular orbital here. Okay. Those two electrons are paired up, okay? So they're just energetically, you have to pair them up, okay? So when you have something like where s orbitals are overlapping and they're just sharing electrons, where it's kind of like a head-on collision. Think of a head-on collision of overlapping orbitals. We call that a sigma orbital. Okay, so this is a sigma bond or a sigma orbital. Okay, and so for an s orbital, it's pretty straightforward. Okay, let me just doodle it here. Okay, so where you have two s orbitals and they overlap kind of like this, that's a sigma. But you can also have p orbitals that overlap. Okay, and they can overlap this way, kind of head on, and that would be a sigma. Or the dumbbells can overlap this way. Okay, and this is called a pi bond. Okay, and this is where you start to have double bonds. Okay, one is going to be a sigma, one is going to be a pi. Okay, we'll get into that a bit later. Okay, so this is an illustration of F2 combining, and so In fluorine, now the orbitals that are involved in bonding are the two p's instead of the s's. And so now this is that head-on collision, and so that's a sigma bond. Okay. So this is an illustration of the HCl molecule where you have a 1s in hydrogen overlapping with a p orbital, and this would be a sigma bond. Okay, because they're overlapping you know, as a head-on collision. That's the easiest way. Okay. All right, so this is kind of a wordy slide. It's just really just describing that covalent bonds are really overlapping of atomic orbitals. Okay, and each of those orbitals will contain one electron of opposite spin. Okay, so just like we showed with the 1s orbitals of hydrogens, okay, they're just opposite spins so that when they do combine, they're paired up. Okay, and each of the bonded atoms, they maintain their own atomic orbitals, but the electron pair is shared by both atoms. Okay, so we're really saying here that these two electrons now, they have come from, you know, a p orbital here and an s orbital over here, and now they're kind of shared between those two orbitals. Okay, and the greater the amount of overlap, the stronger the bond. Okay, and this is where I was talking about, you know, the size of orbitals. If you're overlapping, let's say, something with 1s orbitals, they're pretty small. Okay, you have nice effective overlap. But if you're overlapping something, you know, with 3s or something like that, okay, now there's not as an effective overlap, so the bond will be weaker. Okay. All right, so let's talk about describing some of the bonding in molecules like CH4 or methane. So this is implying that carbon forms 4 bonds. Okay, so carbon, if we were to do the Lewis structure, right, it's this. Okay, but if you look at carbon's electronic configuration, you've got so carbon is 1s2, 2s2, 2p2. Okay, and so this is showing only 2 unpaired electrons, right? So 2 unpaired electrons, that suggests that you would only form 2 bonds. Okay, so how in the world can you form 4 bonds out of that? Well, what happens is that you can get promotion of an electron in a 2s into the empty 2p orbital. Okay, and so you get this configuration. Okay, so we call this an excited state. I guess it's written below, but I like doodling. Okay, so this is an excited state configuration. All right, and now you can see that now there are 4 unpaired electrons. Okay, so this isn't yet quite what happens, because you would imagine, you know, if you have hydrogens coming in, okay, and you've got 4 of those that want to pair up, you're not going to have equal bonding, right? Because one of these is going to bond with a 2s, and then you've got 3 that will bond with a p orbital, so you're going to have not equal bond lengths, right? So you would have maybe one that's really strong, and then you'd have weaker bonds which would be longer or something like that. Okay, so we know that methane, all of these bond lengths and strengths are the same. And so what happens is you have to move from these 4 non-equivalent orbitals, okay, into hybridization. Okay, so you would get a mixture. So this just means mixing. Okay, so you mix the 2s and 2p orbitals. Okay, and you end up, because you've got 1s and 3, okay, so you've got 1 of these and 3 of the p's. This is called an SP2 Hybrid orbital. Okay, and the reason it does that is because now, now you have 4 equivalent orbitals, and now the hydrogens can come and overlap very nicely with each of those 4 orbitals and form 4 equivalent bonds. Okay, so that's an SP2 hybridized configuration, which will give you, if something is SP2 hybridized, it will be tetrahedral. Okay, just like CH4. Okay, so this is a look at this. And so what happens, so you've got an S, and then you've got the 3 different P's, right? So you know that the dumbbells can be arranged along the x-axis, the y, or the z-axis. So you have 3 different types. And so when you have an SP2 orbital, it has lobes. It's still like a dumbbell shape, but if you add this and one of these, then you're going to have a lobe that's a little bit bigger. And so when you have your SP2, so carbon's in the middle here, and now your hydrogen is going to come and bond to each of these SP2 lobes. Okay. Now, since this is kind of a larger lobe, you have stronger bonding than if you just simply overlapped with a P. Okay. And so that's shown here. Okay, so you have your atomic 1s orbitals that are overlapping with these SP2 hybrid orbitals, and that's what your methane structure looks like. Okay, so we wouldn't describe methane bonding as overlap of 1s orbitals on hydrogen with the 2p orbitals on carbon, but it's really 1s overlaps with sp3 hybrids on the carbon. Okay, so that is the way to describe the bonding in methane. Okay, so you can have other types of orbitals, okay, and so you can, what if you mix an S with 2 P's? Okay, so this would be an sp2 orbital, hybrid, okay, orbital, and that leaves a P that's kind of just left, okay, and so what happens is that's where you will end up with a double bond, okay, and so what happens in an sp2 hybrid, okay, which has the shape of trigonal planar, okay, is, so for instance, you know, if you have a carbon, okay, that will form a double bond, okay, with another carbon, okay, so let's look at this structure. It's a hydrogen, okay. This here, this single bond, is overlap of these sp2s, and this, okay, so this is your sigma, okay, because it's a head-on collision. This is a pi because you're overlapping end-on, okay, so it's not a head-on collision, but it's kind of you know, as they're parallel with one another, okay, and so you end up with a pi orbital, okay, which is sideways overlap of a p, okay, and you will have electron density then that is above and below the bond axis, okay, so in this case a pi orbital just adds more electrons between the 2 carbons, okay, so this double bond is stronger than a single bond would be, okay. All right, and then sp hybrid orbitals would be the case where you're overlapping one s orbital and a p, so you have 2 p orbitals that are left, okay? And then you have, so for instance, one example of that would be this, okay, or acetylene, okay, where you have a sigma bond, okay, which is the head-on collision of this time sp orbitals, okay, which are linear. And now you've got a pi from one of the p's overlapping kind of edge ways, okay, and then you've got another pi that is in the other direction. So those are, I guess, the other, so this one, okay. And so if you have SP3, something SP3 hybridization, it will be tetrahedral. If you have SP, it is trigonoplanar. SP2, sorry, it's trigonoplanar, and then SP is linear. Okay, so what type of questions would you get for this? Well, let's look at this. So I could ask you, what's the hybridization of the boron in BCl3? Okay, so for that, you do its Lewis structure. So I think we already did that in a previous slide. So it's this. Okay, so you know that it's trigonoplanar. Okay, so that is SP2 hybridized. Okay, it doesn't have to be carbon. Okay, an example with carbon though would be this one. Okay, so that's, you know, forgetting about all the extra dots. Okay, this is the carbonate. Okay, and that is trigonoplanar. And so this carbon is SP2 hybridized. Okay, and so let me show you another one here. What about this? This is a very common question that you might see on the ACS final. Loves to do questions like this. And I know this is looking very, very complex, but okay, and then let's do that. And just do that. Okay. Now for this molecule, I'm doing the dots here. One possible question could be, how many sigma bonds and how many pi bonds are there? Okay, so if you see a question like this, don't freak out. Just remember that sigma bonds are, again, you know, the head-on collision of orbitals, and they're just all the single bonds. Okay, so counting sigmas, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 sigmas. Okay, and now in multiple bonds, notice, for instance, in this one, okay, I counted one as a sigma, the other one is a pi. Okay, so pi bonds, we've got 1, 2, 3, 4 pi bonds. Okay, so every time you have, let's say, a double, one of them is going to be a single, one's going to be pi. If you have a triple bond, one's going to be sigma, 2 are going to be pi's. Okay, and if it's just a single, then all you have is a sigma. Okay, so that's one possible question, just, you know, counting sigma doubles. The other one would be, what are the hybridizations of things? Let's maybe do this one. Just make one up here. Oops. Okay, and then I guess I needed hydrogen there. Okay, and so I might ask, what is the hybridization at these different centers? Okay, and so the hybridization around the oxygen here. Okay, so how many things do you have around the oxygen? Well, you've got 2 bonds, and then you've got 2 lone pairs, and so this really has 4 electron pair domains. Okay, so it's a bent. Okay, it's a bent geometry, but it has 4 things around it, and so we would really say that that is SP3. Okay, and so the easy way to figure out SP2, SP3, what is it? Just figure out how many atoms are bonded to it, and then take one off. Okay, so for this one, it is bonded, so this oxygen is bonded to 4, or yeah, so it has 4 electron pair domains. Okay, and so if you take one off, that gets you 3, so it's SP3. Okay. Let's look at this carbon here. Okay, so it doesn't have any lone pairs, so it's bonded to 1, 2 things, okay, or 2 atoms on either side. And so if you take, so it's 2 atoms it's bonded to. And so if you take one away, you get 1. So it's SP or SP1. Okay. What's another example? So this one, this carbon, again, no lone pairs, but it is surrounded by 1, 2, 3 atoms. Okay, if you take one away, it's SP2. Okay, same with this one, right? It's surrounded by the oxygen, this hydrogen, and a carbon, so that would be SP2. Okay, so, and then, geometries are from that last table, so if it's SP, it's going to be linear. SP2 is trigonal planar, and SP3 is tetrahedral. Okay, and again, so this would be surrounded by just 2 atoms. Okay, is usually the SP. This is surrounded by 3 atoms, or 2 atoms and the lone pair. Okay, and that would be SP2. And tetrahedral could be surrounded by 4 atoms, or 3 atoms and a lone pair, 2 atoms and 2 lone pairs. Okay, and those are all SP3. So for instance, this would be SP3 for this oxygen. Okay, it's surrounded by 2 atoms, 2 lone pairs. Okay, so that is it for the chapter. I guess you can wake up now. Sorry for putting you to sleep. So when I get back on April, I guess it'll be April the 10th, feel free to ask questions about any of this. I can go through any more examples, etc. For you. Email me, if you can't take the suspense until I get back and something's bothering you about these slides, email me and I can bring clarity to it. But yeah, I hope that this helped, and I will see you in a couple of weeks. All right, take care.